Okay, so can you hear me?
Yes. Yeah, of course.
Okay, so good afternoon,
Yes,
everyone,
we
again.
can.
Okay, great. So, good afternoon. I hope you're having a good day, and we're going to continue with our course on Python for data science. So, before we move on with today's topic, have you all received yesterday's materials, like the zip file with the clustering notebook? So, can anyone please confirm, or at least is anyone there that hasn't really had access to it so that I can repost the links because they've been all the way up because of the chat? Okay, so are we all set with that? Are we all good? Okay, seems to be the case. So again, I am posting the link for today's materials. Oh, okay, so um, for Pitar, let's
You.
give it once again. Okay, so the link above is for the course materials that we're going to check out today. The link below, which has a 2 and 3 dots, is basically the course materials that we saw yesterday. So with that being said, let me share my screen real quick. So I'm guessing that you can now also check my screen. Is that correct?
Yeah, yeah, of course.
Okay, great. So before we move on with classification, are there, for those of you that perhaps actually got a bit of time to spend on the materials, is there any question or anything you'd like to discuss on clustering or any of the algorithms that we saw yesterday? So let me once again move back to the chat to check for questions if there is any. Okay. So if there is any question along the line or in the following days, feel free to always send me an email for questions and whatnot. So feel free to do that. So as a quick reminder of what we've gone through so far, um, I think that we're all pretty familiar with Python and how to set up the language and use V and Vs. So we've actually managed to be able to set up our working environment when it comes to using it for various different projects. We've gone through exploratory data analysis steps through a simple, example by using Iris. And we've also seen how we can actually use clustering algorithms, which is unsupervised learning algorithms on Iris as well as on another, let's say more complex nonlinear benchmark data sets. So today we're going to move on with classification or supervised learning. So before we move on with that, let's actually fire up our virtual environment. So let's go through the basic command that we've actually been accustomed to. So we've opened it, and now let's also go with Jupyter Notebook. So let's wait for that to open. And let's go through, spoilers. So let me restart my kernel real quick so that we can see things together as we go. So just as a reminder, again, when it comes to Jupyter, the strategy that we follow when it comes to setting up our experiments is pretty much always going to be the same. So when we run this notebook right there, for example, the first thing that we got to do is initialize or load our libraries, the necessary tools that we need to use for our analysis. The second thing that we would need to do is initialize some kind of homemade function if we had something like this. In our case, we don't. Yesterday, we saw that there was a plotting function that we created to make our lives easier. And the very next thing that we got to do is basically load our data set. So again, we will be working with Iris. The reason my thing is by now pretty straightforward. It's a benchmark data set. It's not the only, just as a parenthesis here, it's not the only kind of data set that we're going to check out. And having said that, at the 10th of December, we're also going to be working on a real data set, a biomedical data set, in fact, and see what hurdles and challenges come with that. So bear with me on that if Iris makes you a bit, tired. So again, as a reminder, we can check out the different categories that we have, which is something that does matter when it comes to classification, especially, and we're going to be reminded of what classification is in a bit. And then, of course, the other thing that we would need to do, since we're going to be working with supervised learning algorithms, is standardize or normalize our numerical features. So, and the reason behind this is because in a lot of cases, classifiers actually require that you make some sort of normalization, whether it is min-max or standardization, as you see here, or what have you. So since we've already kind of talked about supervised and unsupervised learning, would anyone like, before moving forward, would anyone like to give us like a brief definition of what's really the difference between the two principles? And we're doing this kind of discussion just so that we can actually make things crystal clear and concrete for pretty much anyone. So is anyone willing to give it a try? Like, what's the difference when we're talking about these two different disciplines?
I can go for it.
Yeah, of course, sure. Go ahead.
So, difference between the supervised and unsupervised in the context of this iris would be that when we're doing unsupervised learning, we don't care about the labels because we're trying to get an information out of the data, like cluster them, group them up. And when we're talking about supervised learning, we're talking about classification, where we need to classify. We now we care about the labels if they are which type of iris it is. So basically, um, the supervised has a label and unsupervised doesn't have a label. In short.
Exactly. This is pretty much it. So to add to that, that's not the case only for Iris. This is pretty much the standard procedure that goes through for any kind of data set. So as you've said, supervised learning means that we are taking into account some sort of ground truth. In classification problems, this is a categorical variable that can pretty much represent anything. Again, in the case of Iris, as you've correctly said, it's whether we have a flower that belongs into one of three categories, like setosas or versicolors or virginicas, for example. But it can be whatever other, you might have at hand, like whether, again, my email is spam or not. It could be whether someone is suffering from a specific disease or not, so on and so forth. And again, in clustering, we pretty much forget about this ground truth. We don't really take it into account. In some cases, it doesn't even exist. So what we're trying to do is basically make use of our numerical or even some categorical features that might be available to us in order to be able to group specific samples into distinct teams or clusters. So yeah, this is pretty much the difference. Just as a reminder again, classification falls under the supervised learning category or discipline of machine learning. And another kind of supervised learning strategy would be regression. So both classification and regression, to reiterate, are supervised learning disciplines. The difference between them is that in regression, the target variable is numerical and continuous, which means that it's basically a number. We're trying to make predictions for specific numbers. And in classification, again, it's a categorical variable, and it's pretty much the examples that you can see here in the text in the notebook. So having said all that, Iris, because of the fact that it uses a categorical variable as its target, is basically a data set that is suited for classification. And there are also different types of classification as well. So if we actually have two different values, two different categories that we need to store our data into or classify into, then we would actually call this as a binary classification, because it would almost be like answering to a yes or no question. For example, if my email is either spam or not. And we can pretty much do the same thing with Iris. We can actually kind of simplify what we run with, and we're going to see how we're going to do this, a bit later on. The second type of classification, of course, is multi-class, which is pretty much the default option, especially for Iris, because we don't have two classes, but by default we have three of them, or three different categories that we need to use, in order to be able to make predictions for our samples. So having said that, today we're going to start not with multi-class classification, but we're going to make things a bit simpler. And we are going to start with binary classification using Iris. So in order to be able to do this, we will have to somehow simplify our target variable, right? So the reason why I say this is because, as you can see from up here, we basically have three categories, three different classes, and somehow we need to create two classes out of these, right? So one thing we could do arbitrarily, that is, at least for now, at least in our example, is basically say that we're going to transform this into a yes or no problem. So if a flower belongs to category Setosa, it's going to be a yes. If it doesn't belong to Setosa and it belongs to either versicolor or virginica, it's going to be no. So by doing this, what we actually get as a final result out of this conversion, as you can see right here, is essentially a data set that is now able to be used for binary classification. And the question might be here, is this, right to do? Like, we basically took Setosa just because we felt like it, and then we basically set this as our basis so that we can actually simplify our problem. So is that really correct? Is it wrong? So again, pretty much the answer is going to be a bit diplomatic. It actually depends on the context of the problem. So if we're talking about Iris itself, it's not really that much of an issue because it's a benchmark data set, and Setosas, as we've seen from yesterday's and the day before yesterday's courses, are actually kind of differentiating themselves because they were in the extreme left part of our PCA and UMAP plots, so they kind of differentiate themselves from the other two categories. So this is basically one of the things that we could be using. But when it comes to real data sets, whether we're talking in the context of biomedicine or finance or business or what have you, there might be some cases where a binary classification problem or a simplification to a binary classification problem might make more sense for the final narrative, whether we're talking about research or some kind of a service or a product that needs to be created. So it's not always, that doesn't mean that it's like a panacea and that you should always use this, but it never hurts to basically try it out and see what you're going to get in terms of results. And we're going to check what kind of results that we can actually, get out of this whole process. So the second thing that we need to do, aside from simplifying our problem for starters, is to be able to convert this categorical variable into some sort of numerical representation, right? So the reason behind this is because supervised machine learning models, being computer programs and whatnot, do not really understand, so to speak, of text. They're not really going to understand what yes or no means. So we need to be able to find a way to encode this kind of information into something that will be meaningful for them. So the most meaningful thing we can do is basically use numbers like 0 and 1 for our case, because we're talking about a binary problem. And there are many ways to do this, of course. We could be using a dictionary, as we've seen yesterday and the day before yesterday, in order to create some sort of a mapping, as we actually did for the correlation heat map. Or we can use a label encoder, which will pretty much do things automatically for us. So we actually have many different options when it comes to converting textual type of data or variables into numbers. So if we actually run this example right there, you're going to see that this column, this feature right there, went from being textual into categorical, yet as a numerical representation. So yes is represented by 1, which traditionally for computer science also equals to true, and no is 0, which traditionally equals to false, pretty much. So we now basically have a data set of 150 samples, and we need to find a way to teach, as we've said yesterday, an algorithm how they can actually make correct or precise, predictions for these samples, right? Be able to classify them to their respective categories. In this case, again, just as a reminder, we simplified our problem into a binary classification one. So the classifier that we're going to use, whatever it may be, will have to make precise predictions about whether the sample that I'm looking at is setosa or not, pretty much. So one way we can actually do this is by taking the entirety of our data set and using this in order to basically train our model, right? So this is one thing we could do, but it's not really all that correct. And the reason behind this is because if you use your entire data set to train your algorithm, how are you actually going to evaluate the performance of said algorithm once training is complete? So in order to evaluate your algorithm in such a case, you would actually have to get third-party data from, some kind of a different source. And sometimes third-party data from, many, many different sources is actually kind of hard to come by, right? And that way, what you would have achieved, pretty much what the result of this process would be, having a trained model that we don't really know how it's going to perform. Like, you get something that is trained, but you haven't had the chance to evaluate on previously unseen examples or instances. So traditionally, what's happening when it comes to machine learning models and their training is that we actually take the entire data set and we split it into 2 parts. So one part, or one subset of our data set, is going to be used for training. So during the training procedure, what happens is that we provide our model with our input features, which are going to be, for example, these columns, these 4 numerical columns right there, as well as our target variable, which is the ground truth, which in our case would be not this one, but this one. Basically the numerical representation of our tag. And once training is complete, and this is an iterative process, but let's not delve into technicalities here, right? So once training is complete, what we are actually going to do is evaluate our data on the test set. So what we're basically doing that way is we are trying to understand how our algorithm is going to perform on the previously unseen examples of the test set. And depending on how it performs on the test set in relation to the training, we can either deploy it and create some kind of an application or a service, or go back to the drawing board and either fine-tune our model or perhaps even use a new model right from scratch in case it's not really optimal for what we want to do. So having said all that, are there any questions when it comes to training and its use before we move any further? I'm also checking. Yeah, you could actually do that in order to encode. Oh, so about the converting species to binary. I think there are binary encoders, yes, as part of libraries like sklearn, just to answer that question. But in most cases, the safest way, especially when we are not aware of what the encoder actually really does, is to be able to create these lambda expressions right there. So this particular thing that you see here. So through this, you're able to basically convert your species labels in bulk for all your samples pretty much, depending on a specific condition that you've set out. So this is actually the more well-established way to make the conversion or the simplification to a binary problem, so to speak. And then you can use your label encoder more specifically to basically convert this particular thing into numbers. So this is the well-established thing. But sure, if you actually know how a specific encoder works and how it can perform the conversion itself, and that it does it correctly, then sure, by all means, you could actually use something like this. I mean, there is a wide variety of tools out there. Oh, so you could have a validation part for your data as well. Actually, validation is a very nice touch there. So validation, as Daribor says, would be a third subset of our data set. So what we would actually do for validation is that we would go on and have a third subset of our data set. So in most cases, what you do is that you split your data into training and a rest part, which consists of like 30 or 20% of your data set. And then you split this kind of part into testing and validation sets. So why do we actually use a third set as well? Well, the validation set is actually used in order to be able to evaluate your algorithm's performance on unseen examples during training. So during every single training cycle or repetition, because as I've said before, algorithm training is actually an iterative procedure. So this is basically like you're doing this in order to gain more of an insight as to whether the performance of your algorithm or model actually gets better or worse. And if it actually gets far worse compared to a specific threshold that you can set either by yourselves or by, checking out what other people have done for a specific, domain of expertise or a specific project, then you can basically stop training your model. So this is called early stopping. And this is something that is very well established as a technique, especially for artificial neural networks. So could we actually do the same kind of thing for Iris and for the models that we will be using today? Sure, we could, but because of the fact that it's Iris and because our models are pretty simple in terms of the way they work, and they work quite well, especially on data as simple as Iris, we opted to keep things a bit simpler. So I hope that answers the question, Daribor. I mean, is it clear? And same goes for pretty much anyone else. So is everything clear up until this point as to why we actually get into splitting our data and using a certain part for training and the rest for testing? Okay, so I'm guessing that things are pretty clear because I can't really hear anyone. So how do we actually do this? You get your data set, which is X. This is the input matrix that you have. So basically, when we talk about the input matrix, think of it as this thing right there without your target variable. So these are our numerical features. And Y represents our target variable. So our tag, this thing right there, this array is called Y because this is the output or the ground truth that we need to take into account. And two things here. So the first thing that we do is that we say that the 30% of our data set is going to be used for testing, right? So 70% of our data set is going to be used for training our models. And then we also have this parameter here, which is shuffle equals true. So why do we actually use this parameter? What does it mean for us? So it actually means that when we separate our data set into the training and testing subsets, this separation is actually going to happen randomly. So in other words, it's not going to take like the first n samples and place them in the training set and then the rest of them into the test set, like in a sequential manner. It's going to take random samples from both categories so that we can actually create a more fair, a more objective, less biased training and testing subset in the end. Because what we want to do out of this process is ensure that training is going to be fair for both of the categories that we have at hand, so that our model can actually make as best of a prediction as possible. So first of all, there are many different models that you can use in order to basically do classification. Some models can also be used for regression, but the first one is actually the most well established. I'd say it's actually a very well known model, and it's actually this one right there. So we're going to explain how this actually works. So this is called KNN, or K nearest neighbors. And whenever we mention or you listen to anyone refer to KNN or K nearest neighbors, I want you to think of classification instantly. And the reason why I say this is because in a lot of cases, people might actually confuse KNN for k-means, which is a clustering algorithm. I've done the same mistake myself quite a few times. So how does this algorithm actually work? So first of all, this is kind of a lazy algorithm, so to speak. It's sort of an instance-based algorithm, as we call it. And why is it an instance-based algorithm, you might be asking? Well, because unlike other models, this is not really trained in the classical sense that we might actually think. Like, we're not really feeding it with a lot of data and then making it do predictions. What we actually do, and we're going to see this through an example, is this thing right here. So imagine that we basically have a data set that consists of two different categories. So one of the categories are these blue rectangles, and the other one is these red triangles right there, right? And what happens is that we have a new data point, which is this green circle right there, which basically represents a previously unseen sample. This is our sample, an unknown sample that we need to make a prediction for. So what will KNN actually do in order to be able to make such a prediction, right? It will take into account this point's k nearest neighbors. In this case, as you can see from the black circle, we've taken into account its 3 nearest neighbors. So this would be a 3NN algorithm, in our case, a 3NN instance, so to speak, of the algorithm. So how are the k nearest neighbors defined? Like, which points are the nearest neighbors? And this is basically defined in most cases with a distance criterion. So once again, like in k-means, but again, this is classification here, not clustering, we are using some sort of distance. And in a lot of cases, it can be a Euclidean distance. In some cases, it might be something different, like cosine similarity for whatever reason. But we are basing the annotation of closest neighbors using a distance metric. So we can basically see here that these are the 3 nearest neighbors in terms of distance to this particular point. And then the next thing that the algorithm does is that it annotates a specific label to this sample right there in relation to the majority of the labels of our nearest neighbors. So what we can see here is that we have 2 samples that are red triangles, and then we basically have a blue rectangle over there. So this data point right there would be labeled as a red triangle because the majority of samples, of nearest neighbor samples, that is, are red triangles. So a question that might come up here is what happens in instances where the number of samples is actually of nearest neighbor samples is actually balanced or equal? Like, what if we had a second rectangle, a blue rectangle over here? Or what if we had a blue rectangle and a red triangle and pretty much nothing different? So what would happen then? How would we actually assign a specific label, or the algorithm would assign a specific label to this data point? So in such cases, there are many different things we can do. For starters, the algorithm itself would, in a traditional sense, actually pick one of the categories randomly. So this is the traditional thing to do for the algorithm itself. But one thing that we could also do is actually assign specific weights to the two categories. So we might actually employ a second kind of criterion, like an error function or something similar to that, in order to basically relay to the algorithm that, you know what, this category, for example, the red triangles, is actually more important compared to the blue rectangles. So if you actually have a balanced number of nearest neighbors, you should actually give more gravity to this particular category right there. So are there any questions about how this algorithm works? Anything you'd like to discuss about it? Any sort of feedback before we move on and, run an example for it and how we can actually evaluate the results we'll get? Okay, so is everything understandable up until this point? A bit of a feedback would be quite welcome. Check the chat once again. So, okay. So, okay, thank you, Andrea. So, okay, let's continue. How do we actually go on to use KNN, right? So basically we initialize the algorithm like we do with every other tool that we use. So this is the function that is required for us to use. And then we set the number of neighbors. So again, how do we set the number of neighbors? This is an arbitrary choice. So I chose 20 independently just because I like the number. In real world scenarios and machine learning projects, a very good thing that you could do is pretty much the same thing as working with other algorithms that have a k parameter. So you could either experiment with many different values of k and see which one actually gives you the best result in relation to the project that you're focusing on. The second thing that you could actually do is employ an algorithm optimization function or something similar to that, through which your main goal would be to maximize a specific score, like accuracy, for example, or F1 or something similar. But these are algorithm evaluation metrics, and we're going to check them out in just a bit. So we initialize the algorithm, and then we basically give it to take a look at the samples that we have at hand. And this is an indication that the algorithm is done. Training has been complete. And then we can basically use the test set in order to make predictions, as you can see right there. And we basically see that these are the predictions that the algorithm actually made. So how can we actually compare what the algorithm gave us in relation to our ground truth? So this is where a very powerful tool called the confusion matrix comes in. So let's check it out for our specific example right there with the data set that we have. Okay, so just let me zoom out a bit. So this is a confusion matrix. So what does this actually tell us? What's the result that we are actually getting here? So this is basically a way of visualizing the predictions that our model made. So basically, these are the sample. If you add these up, you're going to get the number of samples that are located within your test set. So this is basically a way of evaluating the algorithm, again, the algorithm's performance more specifically, on the test set that you have. So be careful of that. It's not the entire data set. So what does this actually show us? We actually have the predicted label or the prediction that the algorithm made on the x-axis of our confusion matrix. And then we have the true label or the ground truth on the y-axis here. So what does this really tell us in the end? So it actually tells us that KNN with a k equals 20 actually told us that 34 samples from our test set are considered to be zero, so they're not considered to be setosas. and these 34 samples truly are not Setozas. On the other hand, if we move on down here in the main diagonal, what we see is that KNN actually predicted that there are 11 samples within our test set that are Setosa flowers, and these 11 samples are indeed Setosas. So, in other words, this number right there shows us the instances where the algorithm predicted that something does not belong to the category that we're looking into and that it truly does not belong to that. So this would be a true negative, as you can also see here, because these are truly not Setosa flowers. And these are the true positives. So these are truly positively Setosa flowers. So we have true negatives, we have true positives. So what else do we have here? So basically you see the other diagonal is full of zeros. So it basically showcases that our algorithm actually did pretty well because of the fact that we use Iris. But what would we actually get here in that particular case? Would anyone like to try out, like to interpret the results? So what does this 0 mean, for instance, in accordance to the X and Y axis of our matrix here? Would anyone like to give it a try? Let me also check the chat for a bit. Okay, so let's basically check it out together. This 0 right there actually means that there are no samples whatsoever that are predicted to be as Setosas, but are truly not. So this thing right there would actually be considered as the false positive because the algorithm would actually predict that it does belong to this category when in reality it doesn't, right? And these right there would be the false negatives. Like the algorithm would actually predict that the samples in this particular category right there are Setosas or are not Setosas, sorry, but in reality they are. So what do we actually want ideally in order to deem an algorithm suitable for, deploying it as part of a service or decision support system, for instance? So we would actually want our algorithm to have a very high true positive and true negative value and extremely low false positive and false negative values, right? But the thing is, as we've seen with Iris, like this is an ideal example because of the fact that it's a benchmark data set. So the thing is, if we actually have to choose between false positives and false negatives, like is there any way to prioritize like the minimization criteria? Like which one would we like to be lower and why, for instance? So that actually again depends on the context, but in most cases, we would actually want to have a far lower false negative compared to the false positive. And the reason behind this is to put it all into a bit of a context. Imagine a biomedical problem, for instance, right? So you basically make a classifier, so you have a machine learning model, and what? Was there anything you wanted to say? No? Okay, so if there is anything you want to comment on or add to that, so feel free to do so because I cannot really see the chat right now. So as I was saying, imagine that we have like a biomedical problem, right? We basically train a model which can predict whether a person suffers from a very severe disease or not. So the output of the model is either 1, which indicates that yes, you do suffer from said disease, or 0, which means that no, you do not really suffer from, said disease. So we would actually, in such a case, like to have as low of a false negative value as possible, because a false negative would mean, for our case, that the model predicts that the person does not really suffer and that they are healthy, when in reality they actually do suffer from the disease. And this can actually have very grave, problems and consequences for people's quality of life. And the same pretty much applies to many different other domains of expertise. So, does that mean that having a high false positive value, especially in the context of the problem that we are describing, is something that we would want? Ideally not, but at least a higher false positive value would mean that the model predicts that someone has the disease when they really don't. So at the worst case, they would basically be a bit scared at first, but then they would go on and check further through a second examination, perhaps, or a third in some cases, and basically confirm that they are, healthy and that they're not really going to have, any kind of problem down the line. So you do have to minimize both. That's the takeaway. So you do want as low of a false positive and a false negative as possible. But if you really have to choose, I'd say that in a lot of cases, you'd want a lower false negative value. But that, of course, depends on the context of the problem that you're trying to solve. And just to move things a bit further, the confusion matrix and these true positive, false negative, false positive, and true positive values that you see here are actually used in order to create certain classification evaluation metrics. So the most prominent one, of course, is accuracy, for example. And you can see how accuracy is actually, calculated. So you take the true positives, and then you basically take the entirety of your predictions right there. So whether they are true positive, true negative, false positive, or false negative. So basically what happens is that this is a way, accuracy is basically a score that signifies that a model is able to predict what's going on between your two categories accurately, especially for unseen samples. So this is the most prominent type of score that you're going to see on pretty much any machine learning project. Does that mean that this is the only kind of metric that you should be using for your projects? Well, the answer to that is no, definitely not. So you'd want to use some things more. So all of the scores that you see here, like precision and recall and whatnot, they're all, once again, let me reiterate, calculated through the values that you get from your confusion matrix. So this matrix right there, or this one if you prefer a more generalized representation, is basically the basis for the types of evaluation that we're going to run, later on down the line. So you basically have other scores. You basically have precision, you have recall. You can basically see what these mean right there. I don't really like reading from the notebooks from the notes, but basically precision means that of all the instances that you predict as positive, how many are truly positive. So it's a way of understanding further whether your classifier predicts if something is true, if it truly is. So it's a way of going through positive predicted values, I guess. And the other one, as you can see here, is recall. And then there is also F1, which is basically a combination of the two. So in most cases, when it comes to projects or even research papers, again, accuracy is not enough on its own. So you would either have to use accuracy and then one of these two, or maybe both scores, or you could actually use accuracy and then basically go for the combination. Like this is also called the harmonic mean between precision and recall. So F1 is considered to be that. And then there is also a third score that you could be using, or a third metric, a third sort of tool that you can use to do this, which is the receiver operating characteristic curve, which is this kind of blue line that you see right there. So what does this actually mean? What does it show us? So you basically have the false positive rate on the x-axis. This is basically a ratio of how many predictions are false positive. And then you basically have the true positive rate, or the ratio of how many true positives the algorithm predicts. And what you actually want to do with this is that in ideal cases, you'd want your false positive rate to be as close to zero as possible, which is pretty much the thing that we can see here with Iris, of course. And then you would want your true positive rate to be as close to 1 as possible, or to put it all into percentages, 100%. So in ideal cases, which is pretty much what we see here, again, because Iris is a benchmark data set, so we would expect a performance of such scale out of such a data set, is a line which goes upwards and then all the way to the right. And in order to be able to put this into a score, like to be able to see the numbers behind this, we can also get the area under the curve. So if we actually map this area under this blue straight line thing over there, we're actually getting the area under the curve, or the AUC score. So the higher the AUC score means that we have a very wide area covered by this line, which is ideal for us because it shows that our model is able to perform really, really well. So we can also use accuracy, precision recall, F1, as we basically said before. So there are specific functions to do this through scikit-learn, for instance. So if we actually run these, and in order to do so, you need to use your ground truth as well as the prediction that the model made. Again, these are based off of the test set, of course. And what we see here in all cases is that we get a score of 100%. So this is actually, I'd say, pretty remarkable. I mean, someone could say that this is actually pretty impressive as far as performance goes, but we should always be reminded that this, once again, is a benchmark data set, and it's so simple in terms of the patterns that it includes that such a performance would be expected. So in other words, if we were to propose a new classification algorithm and we were to test it on Iris and it didn't perform that way, then that would actually mean that we are doing something very, very wrong. So with that being said, again, sorry if it's a bit tiring, but are there any particular questions, anything you'd want to discuss up until that point for what we've seen? Okay, so I'm guessing everything is clear so far?
I would like to hear again just one more time about the confusion matrix. So we say that true negative is the ones that are predicted that does not belong. We said, and the true positives are the ones that belong. Can you please tell me about the false positive and false negative again?
Yes. So essentially, let's reiterate over there. So what is actually a false positive and a false negative, right? So a false negative means that the model, the predicted label that we got from our trained machine learning algorithm is 0. So the model pretty much tells me that a sample does not really belong to Setosa, for example. So it gives me an answer of no, when in reality, the answer of the binary tag that I have, because we are talking about a binary problem, the ground truth is yes for that particular sample. So in other words, the algorithm predicts that the target variable is no, when in reality it's yes. So this is actually a false negative. This is why we call it a false negative, because it's not really negative, but the algorithm tells me that it is, right? So the false positive is pretty much the exact opposite. So the algorithm tells me that the target variable has a value of yes, when in reality, the ground truth, or the reality of our data set, pretty much tells me that no, the answer is no, it's not yes. It does. So in the context of Iris, and taking into account that we've actually simplified the problem to whether a flower belongs into Setosa or not, a false positive prediction would be my model to tell me that a particular flower belongs into the Setosa category, when in reality it actually doesn't. So this is what a false positive and a false negative means. So why do we actually, again, just as a reminder, why would we actually want to have a lower, false negative in comparison to our false positives, right? So it might not, make that much sense for Iris because, again, it's a toy example, but it does make an awful lot of sense in, real projects, in real data science applications. So the reason behind this is because in a lot of cases, it's better to actually get a red flag from our model, even though it's wrong, so that we can actually test things further, especially in the context of life sciences. So it's better to actually have a model with a higher false positive rate compared to a false negative rate, because a false negative, again, in the context of life sciences, for example, you'll see me mentioning this a lot, but this is basically my field of research. So in such a case, that would mean that the model actually tells me that a certain person or a cell or a specimen, for example, does not, for example, suffer from a disease, or something does not really happen, does not occur, when it in reality it does. And this can actually lead to people, whether it is doctors, biologists, or patients, to actually leave the problem as is in some cases, because some people might trust such systems because of the fact that they're machine learning and AI completely, or not in some cases, but whatever. And this might actually lead to very grave circumstances and consequences for the quality of life for people. And the same thing can be said for other things, like, for example, in the manufacturing industry. So this kind of false negative could mean that a product is not defective when in reality it is. And depending on the product, this can actually again cost gravely for specific people. For example, the product might be a car, or it might be a furnace, or something different. I don't know. So is it a bit more? Is it a bit clearer? Is it a bit more
Yes, it is.
understandable now? Okay,
Yes,
great.
thank you.
Great, you're welcome. So this is why we actually, so again, does that mean that we want to have a high false positive for whatever reason? No, I mean, in ideal situations, we would like to have low false positives and low false negatives, right? We would like to have as low of a score for both of these things as possible. But if we have to make, again, a trade-off, I would say that seeing a lower false negative is actually going to result in a more meaningful model compared to having a bit of a higher false positive. But again, a very high false positive can also cause very serious problems. So if we see something like this, we would probably have to go back to the drawing board and either fine-tune our models or use another classifier entirely and pretty much start our experiments from scratch, right? So with that being said, let's move on to the second model that we're going to be using, support vector machines. So support vector machines, just to put it down to a bit of a history, before artificial neural networks and other types of classifiers and whatnot, they were the craze, especially in the late to mid 90s and early 2000s, right? So what is a support vector machine? So it's a model that can be used both for classification as well as regression. But of course, we're using it for binary classification now, right? So how does it actually work? Okay, so imagine that we have, once again, a binary classification problem. So we basically have these samples right there. So we have this class right there of samples, and then we have these ones as well. So as you can probably see, these two categories can be separated from each other by using a straight line. So this is a simple, problem that can be solved with a linear model. The problem, however, is that there are many different lines, many different straight lines that we can draw in order to be able to, separate these two categories. So how can we actually find which is the most ideal line that we can use in order to make the best possible separation between these two categories, right? So support vector machine actually tries to find the line. So again, I'm not delving into the technicalities and the maths of the algorithm just to make things a bit more high level for everyone. But what it actually does is that it picks out of all of these lines the one that actually has the maximum amount of distance from all samples, no matter the category that we're running with. So as you can see here, for example, in our case, this would be this green line right there. So why do we actually have these two samples from our two different categories into circles, into these black circles? Because in order to make this choice, the algorithm will also take into account the samples that are actually the closest to this line. And they will actually pick, the algorithm will pick the straight line that is able to have an equal distance between the closest points, so that it can actually ensure that it's going to have the furthest possible distance, for all other points as well. So essentially, to reiterate, to make things a bit simpler, we want to make sure in this case that the line that we're going to draw in order to separate our categories is not closer to one category over the other. We want to be exactly in the middle, or as far away as possible from both of them. And the reason why we actually circled, again, these samples is because these are actually the ones that play a very important role in order to determine which is the correct line to use. So these samples are called our support vectors. Why do we actually call them support vectors? So the support in support vectors actually has to do with proximity. So this means that they are basically, it's a fancy term to basically explain that these are the closest vectors to the possible separation lines that the algorithm creates. So why do we call these vectors, since we're talking about samples? Well, the reason behind this is because a sample, in reality, if we go back to our matrix, is essentially nothing more than a feature vector. So a sample, so for example, sample 0, or the first sample within iris, is nothing more than a vector of specific values. So our features are our vector values within this. So if we were actually to take this particular sample on its own, we would also call it as a feature vector, hence the name support vector. And machine pretty much refers to the fact that it's a machine learning algorithm. It's a classifier. It's basically, a fancy term that we use to make the sound, or to at least make it sound back then as, great and futuristic and whatnot. And to be quite honest with you, it kind of was. I mean, back then when we didn't have the computing power to use, big and complex artificial neural networks and other models such as gradient boosting trees, for example, and whatnot, this algorithm was king, pretty much. And the other reason why it was really effective, and still is to this day in some instances, is because of the fact that it can be used effectively even in nonlinear data sets. So take this example right here. So we have a data set that consists, again, of two categories. But as you can see, in 2 dimensions, we actually have a very complex kind of pattern going on through it, right? So if we were actually going to separate these two categories from each other, at least in a 2-dimensional format, we would have to use some kind of a nonlinear model, right? So support vector machines actually do away with this. So what a vector machine would actually do in such a case is that it would actually lift this data set from 2 dimensions to 3 dimensions. And in some cases, the third dimension can be like a linear or a nonlinear combination of the X and Y axes that we have over there. It can be many different things, but it basically lifts your data set into a third dimension, like a higher dimension than what you start out with, where in reality our samples can be pretty much separated, because as you can see, even though things do not seem really clear in 2 dimensions, I can basically see here that if I actually have this sort of blanket, this sort of hyperplane created, I can be able to separate my two different categories very easily. So this particular attribute that support vector machines actually have is called the kernel trick, like the ability to lift the dimensionality of the data set in order to be able to account for more meaningful separation patterns, at least when we actually know that separating in the current format is not really all that possible and would require a very complex model. So back then, it made a lot more sense because we didn't have access to extremely complex and computationally expensive models. So right now, a lot of people might have gone to something like an artificial neural network with a very deep architecture for a very complex model such as this, or a problem such as this. But we should always remember that support vector machines are computationally more efficient or less expensive, so to speak. So this might actually be very important for what we're trying to do, especially if we do not have access to like a GPU or an awful lot of RAM, for example. So having said that, are there any questions about support vector machines and how they work? I'm sorry if this is like a handful, but I'm trying to make it as high level as possible. So again, is everything understandable up until this point?
Can you repeat going from the 2 dimensions to 3 dimensions?
Yes, of course. So again, imagine that you have a nonlinear problem such as this, right? So what support vector machines would actually do, provided that you specify the correct arguments, which is basically assigning the correct kernel to them, like a nonlinear kernel, is that they would actually take this two-dimensional data set, for instance, and they would actually lift the dimensionality from 2 to 3, so that they would actually basically add a third dimension. It can be many things depending on the kernel that you use. It can be, for example, a linear combination of the existing dimensions that you have, or a nonlinear combination of your already two existing dimensions. So the reason why it does that is to basically be able to provide for a representation of our data set such as this one, like in 3 dimensions. And this actually makes sense because a data set that might seem kind of chaotic and complex in 2 dimensions might actually seem quite separable and simple in a third dimension. And of course, the same pretty much applies if you have like 4 or 5 dimensions in your data set. Of course, in 4 and greater dimensions, we cannot really see what's going on, but it makes sense, at least, mathematically speaking. So in such cases, instead of actually creating, like a separation line as it would in 2 dimensions, it actually creates like separation hyperplanes, which is like this green, let's say, solid kind of blanket thing that separates our 2 different categories. And the reason why it does that is to be able to account for the complexity that is in some cases inherent into, some data sets that we might have. So this is
But
pretty much why we...
Yes, but the axis, like from what I understood in the 2D plane or 2D plane, it said like one axis is, for example, the fatal width, and the other one is something else. And here you are just using something like new vector, or very good. Can you get the first volume?
Yeah, so essentially, if you had the petal width and the petal length, in the case of Iris, for example, and you had these 2 features, by basically employing the kernel trick, you would employ a third dimension, which would be like a linear or a nonlinear combination of these 2 features. So imagine it pretty much like what you would have with PCA, for example, where we actually said that the vectors that we have are not our initial features. They are basically some kind of an algebraic combination of what exists. right? So it can be linear, like in PCA, for example. It can be nonlinear, like in TSNE and UMAP, for example. And this is pretty much a parallel kind of, I'd say, application as in the visualization stages that we've seen earlier. So it pretty much has to do with what we've seen in the main principle as to if I have a PCA plot in 2 dimensions and I see something like this, I might get a three-dimensional version of said plot, and things might be far clearer as to how my samples are, grouped together and how they can be separated together. So pretty much what support vector machines do is that they take this into account, and or the people that created them took this into account and basically made use of the same kind of criterion in order to move further with, as a workaround for more complex classification problems. So, but it can pretty much be many different things. That depends on the kernel. And the reason why I say that it depends on the kernel is because the kernel is pretty much the argument that you would have to set to a support vector machine. So it can be a classic linear kernel, which means that it will take the starting dimensionality of your data set and either create a line if it's a 2-dimensional data set, or some kind of a hyperplane if it's 3 dimensions or more. Or you can give it some kind of a kernel trick, so to speak, kernel, which can either make linear combinations of your features in order to increase the dimensionality to a higher dimension, or a nonlinear one. So I don't know if that answers the questions. I got ahead of myself.
It does.
So. Okay. So
thank you.
Okay, you're welcome. So let's actually see if what's going to happen if we actually use a nonlinear kernel, for our support vector machine, right? So how is it actually going to perform on the Iris dataset in our case? So again, just to make things clearer, this particular example that we've seen here is, more for illustration so that we can get a good understanding of what's going on with the model. And it's not Iris. That's what I'm trying to get at here. So these illustrations are, just for the purposes of understanding, of getting a good, let's say, initial theoretical basis of how this model works. So now we're testing it on Iris. So, and we're using a nonlinear kernel in order to do so. So we specify our kernel, and then we basically fit the model. We train it, basically. So training is complete. The reason why you see training being complete so fast is because of the fact that we have a fairly small data set. So if you try to use support vector machine on a larger, more complex type of data set, it will take an awful lot more time, especially if you're using a nonlinear kernel on a big data. And then you can, of course, make predictions on it, and then use a confusion matrix once again, right? So we pretty much get identical results, if not the same, as what we get with KNN, right? So the question might be here, which model, considering that I get the same performance for this data set, which model should I actually be using? So in a sense, if I have 2 or 3 or n models and they all perform in the same manner and they all perform really, really well, which one should I actually pick? So let's keep this as, food for thought for now, and we're going to answer this question during the end of today's course. So again, just to move on a bit.
It depends on the data that we have every time, huh?
Yes, so yeah, so okay, a bit of a spoiler here, but yes, it depends on the data set.
Sorry.
And no, it's okay, it's fine. It depends on the data set, and it also depends on other things. So another criterion that you could say that actually plays a very important role, especially in big data, is, for example, the computational time that is required for your model to run. So if you actually have 2 models and they perform in the same or very, very identical manners in the same data set, then it would most probably make sense to pick the model for your final application or your service that is actually computationally more efficient, so more economic, so to speak, the model that actually consumes less RAM and perhaps even less GPU RAM as well, if we're talking about a very complex kind of a neural network kind of thing. So we're actually going to see this a bit further and basically try to give more of a better interpretation of what's going on. Like, why would we not want to use like a nonlinear model in such a case? So again, as you can see here, we get the same pretty much results as we got with KNN. So once again, we get amazing performance, but as a reminder, once again, this is expected because we are using a benchmark dataset. And in real world scenarios, in real world data, be it binary or multi-class classification, we would have gotten far worse results than what we see here, of course. So the third model that we are going to check out today is basically decision trees. So let's move lower so that we can actually have more of an illustration. So a decision tree is something like this. It's a mathematical model that tries to basically mimic like dilemmas, so to speak, right? So this is the root of the tree. This is the starting point of our tree. And what basically happens is that we take into account a specific feature that we have within our data set, like a specific column, and we basically check whether this column has a value which is either lower or equal to a specific threshold, which is arbitrary for decision trees. It can be, it's actually initialized in a random manner. And then we check out pretty much what happens for the samples that we have within our data set. So if the value, for example, for this particular feature is lower or equal to the threshold, then we say that yes, it is lower. So we move to the left of the tree, for example. Or if it's not, if it's greater or equal, then we say no, it's not. So we move on the right side of the tree. So why do we actually, and then of course we move on further down the line until we conclude into leaf nodes. So leaf nodes basically include samples, and ideally, if we're talking about a very accurate predictor, they should contain samples that belong into one specific category. In other words, our leaves must contain samples that only belong into one of the categories that we start out with, be it setosas or not setosas, be it virginicas or what have you, just to, include every possibility, whether we're talking about a binary or a multi-class problem. So why do we actually use like decision trees? Why does this matter for us? Well, the answer to this is because decision trees are actually very simple and easy to understand, especially compared to, other more complex models. Because when a decision tree makes a specific prediction, you can also check out the illustration that goes on, behind the lines. So you can basically check this kind of a rule-based system that the tree created during its training, so that you can actually understand how it made the prediction that it did. And then, of course, there are other specific measures that we use within trees. There is entropy, for example, which showcases whether the split that we do into different, dilemmas right there is clean, or in other words, to reiterate, whether it consists only of samples that belong into one category. And then you basically have other things like impurity, which measures pretty much an identical thing. So again, why do these measures actually matter for us aside from interpretability? Well, the reason for this is because decision trees are also actually include embedded feature importance. So what that means for us is that during training, because of the fact that we use different features, to make the dilemmas that we've talked about for every node of the tree, the decision tree actually manages to infer which of the features are the most important ones, the features within our data set that is, to make the final correct prediction that we might run ourselves into. So The reason why this might be, valuable for us is in the context of feature selection. So instead of actually going for, a more computationally expensive algorithm like a wrapper-based feature selector, and we're going to see what these are in a future lecture, or a simpler statistical test, we can employ the same model that we use for predictions, for basically inferring to which category our samples belong to, as a predictor as to which features actually contribute the most to this final decision. Hence why they're actually very important. And just so that we can actually run an example, you can see that initializing it, let me zoom in a bit. So initializing it again is very simple and easy to do. So you initialize the model, you train it, once again, same thing. It runs really fast, again, because of the data set that we use. You get a number of samples right there. This is the training part, and then you make predictions on it. You get the confusion matrix. Again, same pretty much result that we got with the other two algorithms that we run because of Iris. Same kind of performance. Once again, the receiver operating characteristic curve is also the same. So again, ideal performance. The same goes for our other scores, but what this thing has, what this algorithm produces aside from these results, is something like this. So this is in our case, the decision tree that has been created for our own data set. So you can basically check here that the feature name that we used was petal width. So this is basically the feature that we've set up for our threshold. And the algorithm basically inferred that the value that should probably be used, which is done arbitrarily at first, but okay, is this one right there. This is the normalized value. Once again, this is why it's negative, right? So we get the impurity right there. This is Gini impurity. So this basically means that this essentially varies from 0 all the way out to 0.5. So the lower the value, the more pure our split is going to be, which means that the node is actually going to have samples that belong into one specific category. And what we see here is that unfortunately that's not the case, because we have 66 samples that belong to one category and then 39 that belong to the other one. But the class that we start out with, the predictor that starts out with, is not Setosa. And what happens is that because of this threshold, our tree manages to create two resulting nodes, or two leaves, that basically manage to separate our test set into two specific categories. So it manages to use this particular feature and this particular threshold to go from this node right there, which has this kind of impurity and this number of samples and this kind of prediction, of course, into two separate ones, two leaves that are 100% clean. They have a Gini impurity of 0, which means that they are pure. They do not really have samples from both categories. You see that you have 39 samples that belong into the category Setosa. And then you also have 66 that belong to the other category, which is no Setosa, pretty much. So, of course, this is a very simple tree. This is considered to be a shallow tree because we moved on from our root directly to the leaves of the tree. So we didn't have any intermediate nodes as we would have right there. And the reason why we got this is because of the nature of this data set, as well as the parameter initialization. In our case, we didn't really initialize any parameters. So we basically used the default options that are available within sklearn. So in other kind of situations, we might have wanted to also specify the number of nodes that the tree will produce, as well as the number of samples that will be taken into account for each node. But again, as we've said before, there is no ideal number or value that needs to be used for initialization. This is more like a trial and error thing, or something that we would be doing through the use of a specific kind of scheme through which we would like to optimize, a specific objective. So having said that, is everything clear as to how, or at least as clear as possible as to how decision trees actually work? Are there any questions on that? Something that you would like to, discuss up until this point? Oh, sure. Yeah. Let me actually give you the link to it. So I got you covered. So give me a second and I'll, give it to you right now. Okay, so there you go. Right, so let's actually have a very short break for a breather and perhaps even a glass of water. And we will be back in about 5 to 6 minutes. So 5 minute break, and then we continue with the final part for today's lecture. So see you in a bit. Okay, so can you hear me?
Yes.
Okay, great. So let me also share my screen real quick. So let's get back to it for the final part. So basically what we've seen so far is how we can actually train and then evaluate. So you can also see my screen before I move on. So, right?
Yes.
Okay, great. So um, we've actually said that we can use train test splitting and perhaps even train test and validation splitting in order to train and subsequently evaluate the classifier that we're going to use in our data set. So this is one of the things that we could be doing. Is there any other alternative that we could actually do when it comes to training and evaluating our model? And the answer to that is yes, there's actually k-fold cross-validation. And let's see this illustration right there. So this is actually an alternative way of training and evaluating your algorithm, especially in cases where your data set is actually pretty limited in terms of samples. Like when you actually have very few of them, because truth be told, machine learning models work best when you actually feed them with large amounts of data or samples. Like even 1,000 samples, just to put it all into a bit of context, is considered to be too little for most of today's, projects and problems. So in a lot of cases, we could be using something like this thing right here. So like cross-validation, what do we actually do with this? So we actually, again, this is an iterative process. So what happens is that we split our data set into two parts. So we basically use training and testing once again, but now the process is iterative, but in a different way. So we create k different folds. In this case, in particular, if we actually had iteration 1, 2, 3, and the final one that you see here, we would have 4 iterations. So 4 repetitions of this procedure, or 4 folds if you prefer. So what happens in its case in each fold is that a particular percentage of your data set is used for testing. For example, the 25% of our data, so like 5 samples out of 20 in this particular case. And what happens is that an instance of our machine learning model is created, and it's actually trained and subsequently tested on the data that we have according to the split that we've made. In the second iteration, what actually happens is that, again, we split the data into training and test sets, but now it's like we have a sliding window that moves towards a different subset of our data that should be used as the test set. So you can see that in the first iteration, we've used these particular samples to serve as our test set. In this second case, in this second iteration, these are the samples that we're going to be using in order to infer or to evaluate our model. And the rest of them outside of this bounding box are going to be the samples that we use for training. And then, of course, we move on. So then in the third iteration, these are the samples that we'll use for testing, and then the rest are going to be used for training, and so on and so forth. So basically what we do, imagine as if we are actually using a sliding window in order to be able to make specific cuts into training and test sets for our data set. And the reason why this is actually considered to be a more effective technique when it comes to evaluating our algorithm, especially in cases where the number of samples is limited, is because by the end of this process, we are actually going to have a model or many different instances of a specific model that will have been trained and evaluated on the entirety of our data set. Each of them is going to be, of course, trained and tested using different subsets, but again, we will have different instances of the same algorithm, that at the end of the day will have considered the entirety of our data. So our entire 150 samples, for example, in the case of Iris. So what do we mean by instance, a model instance? So imagine that for example, take support vector machine or random forest, for example, right there. So this particular thing, or decision tree, sorry. So the decision tree would actually be the blueprint that we have. And when I initialize it right there, when I actually create the classifier, this is an instance of our model. So it's basically like taking a blueprint and creating a specific particular, batch or, version of that blueprint. So what happens, for example, if I use cross-validation in combination with decision tree, what would actually happen is that I would have, in this particular case, for instance, 4 distinct instances of a decision tree, each of which would have been trained in specific and tested, of course, in different subsets of training and testing, of course. And how would we actually be able to evaluate the results that we get out of this process? We would then take the accuracy, the F1 score, and perhaps even the recall and precision that we would have from each and every one of these iterations, from each and every one of these folds. And we would do 2 things. We would calculate the mean, or the average if you prefer, and we would also calculate the standard deviation. So we would actually calculate the mean so that we can see, on average, in relation to every single one of our folds, the performance of our model. And we would also check the standard deviation in order to be able to understand whether said performance is actually consistent enough for what we're trying to do. So what would we consider to be consistent enough? That depends, but in a lot of cases, you would have like a standard deviation, which would be as close to 0 as possible. Like 0.05, for example, would be a very good starting point for what you want to do. So what we are going to do in order to test this particular, method of operation is we are actually going to create a deep copy of our iris dataset, as you can see here. This time we're going to make it multi-class, so we're going to use the entirety of our categories, and we're going to use again a standard label encoder. And as you can see here, the difference is that instead of having 0s and 1s, we also now have 0s, 1s, and 2s for our 3 different categories. And then, of course, we can use this function, which is called cross-val score, in order to be able to run cross-validation. So there are many different functions to run cross-validation through sklearn. One of them is cross-validate. The reason why I really like this one is also because you can set many different scoring schemes through there. So I can use accuracy, but if I set, my evaluation scores in the form of an array or a list, I could also set, for example, F1 score. I could set something like the area under the curve, like, for example, rock AUC, and so on and so forth. But for now, let's just go with accuracy. Right? Let's just use this, so that we don't make things all that complicated. So, okay, we got an error. So why did we actually get an error? Well, the reason for that is because I forgot to delete these brackets right there. So as you can see, if I do this correctly, this is the kind of result that I get. So what are these right now? This is a vector that actually represents the accuracy score that I got for each of the 10 folds that were created. And I can use this, or I can run it again. And this time I can actually print out the mean, or the average, pretty much. So out of this whole process, through cross-validation, I get an accuracy of like 94.6%. And why do we actually see this difference between this particular method and what we had earlier, with standard train and testing? Let's not go up there. It's pretty bad. It's a pretty bad idea because we have a lot of slides and whatnot. So the reason is, first of all, or first and foremost, because we changed the narrative or the problem. So we moved from a binary classification problem to a multi-class classification problem, hence the difference in accuracy. If we round this up, it would be like 95%. So another thing, just to tackle something right out of the way. So what is considered to be like a good accuracy score? And that, again, depends on the context of the problem. So if you are running into a binary classification sort of project, an ideal accuracy score would be something like very close to 98 or 99%. In a multi-class classification score, in a multi-class, problem, an accuracy score of like 95%, and maybe in some cases a bit more than that, is more than ideal, because we always have to remember that we're dealing with more than two categories. And in some cases, these categories can also be imbalanced, or they can be many more than just three. So another question that might pop out is, what happens if my data set is imbalanced, right? What happens if I actually have 3 or 4 different categories of samples and they're not equally represented within my data frame? So there is actually a version of cross-validation that is called stratified k-fold cross-validation. And let me also write this in the chat, so just so that you can actually check it out in case you want to. So the main difference between this particular cross-validation that we see here in this illustration and stratified k-fold cross-validation is that through the second one, what will actually happen is that the training and validation algorithm, of course, will make sure that the distribution of samples within each fold is actually representative of the entirety of our data set as a whole. And the reason why this is important is because we're actually splitting randomly into training and testing subsets, and this can actually sometimes create bias. So by basically keeping the distribution of samples into different categories as stable, we manage to somehow actually, in most cases, actually minimize said bias and have more objective, more accurate, more precise results. Right? So this is another thing that we can actually account for. So at the end of the day, again, which classification algorithm should we use? It actually depends as a final, conclusion on the problem. So if you have a very simple linear problem, so it actually depends on the data set, as one of you actually said very correctly, before the break. So if you have a simple data set that actually has linear patterns, which you can find and highlight through a dimensionality reduction technique, perhaps like PCA or perhaps even UMAP, for example, then it would be best to go for a simple, well-established algorithm, something like a KNN, for instance, or a simple decision tree, or perhaps even a support vector machine with a linear kernel. If your dataset has, very weird, intricate, nonlinear patterns within it, then you should probably either try a support vector machine with a nonlinear kernel. You could also, try your luck out with a decision tree, or you could go for more complex models, such as, random forests, which are basically ensembles of, decision trees. But we're going to check what an ensemble is, in a different lecture. So why would you not want to use, again, just to reiterate, a very complex model on such a simple data set like Iris? Because it simply will not really make a difference. The only thing that you will achieve through this is to basically, eat away parts of your memory and your VRAM if you're using something that is also supported by a GPU. It will basically be like, going out to hunt rabbits with, an artillery cannon, for example. So in a lot of cases, you should also consider the complexity of your problem. This is number one. And the second thing, the computing power that is required by the models that you're going to use, and subsequently in relation to the data set that you use. Because a very complex data set, if you actually combine a very complex data set with a lot of samples and an awful lot of columns or features, with a very complex model, you're in for a treat. I mean, it's going to be a hell of an experience, and I'm not saying this in, a positive way. So with all that being said, this pretty much wraps it up for today's presentation and lecture. So are there any questions as to the things that we've seen so far? Is there anything you'd like to discuss? Was everything understandable? Any kind of feedback would be more than welcome. No, thank you very much, Matei. I mean, for your applause. So, thank you, Andrea. Thank you. So, if there are no questions or anything else you'd like to discuss, I thank you very much for, being here and bearing with me, even though it's very close to 7 o'clock set time and like 8 o'clock here in Greece. So I hope you found today's lecture interesting and helpful somehow for what you would want to do in the future, or in case you're currently running into a machine learning project. And I'll see you guys tomorrow. So just as a small spoiler, tomorrow we are going to occupy ourselves again with classification and clustering, but we are going to see how these processes are automated through a library which is called PyCarry. But I think you're going to like it, but we're going to see tomorrow. I don't want to spoil things too much. So with that being said, thank you once again, and I'll see you tomorrow. So take care. Have a good evening.
Thank you.
Thank
See
you.
you around.
Goodbye.
Thank you.
Thank you very much.